There is a moment every summer when a room seems to turn against you. It usually happens late in the afternoon. The air conditioner is running, the curtains are closed, the thermostat is set exactly where it was that morning, but the temperature keeps rising anyway. Stand beside the window, and the reason becomes obvious. The glass feels warm, the floor beneath it feels warm, the furniture sitting in the sunlight feels warm. Even after the sun moves away, those surfaces continue releasing heat back into the room. Most people respond by lowering the thermostat. The machine runs longer, the electric meter moves faster, the room eventually cools down, but nothing about the window is changed. Tomorrow afternoon, the same process begins again. We tend to think of windows as passive parts of a building. They provide light, a view, and a way to open the room to fresh air. But thermally, a window is not passive. It is part of the machinery of the house, and in many older buildings, it is the least efficient part. Walls can contain several inches of insulation. Attics can contain even more. A window may contain only a thin sheet of glass, separating conditioned indoor air from the weather outside. That difference creates a weakness in what engineers call the building envelope, the collection of walls, ceilings, floors, doors, and windows that divide the inside of a structure from the outside world. The better that envelope performs, the less work the heating and cooling equipment has to do. The weaker it performs, the more machinery must compensate. This is why an air conditioner can operate perfectly and still struggle to keep one room comfortable. The system may be removing heat exactly as designed, while the building continues collecting more heat than the system can remove. Sometimes the problem is not the machine. Sometimes it is the barrier. And one of the cheapest ways to strengthen that barrier has been sitting inside shipping boxes for decades: bubble wrap. To understand why packing material can affect the temperature of a room, forget the plastic for a moment. The important part is the air. Air is not a particularly good conductor of heat when it remains still. That is why many forms of insulation do not work by creating one massive solid wall. They work by dividing air into countless small spaces where it cannot circulate freely. Fiberglass insulation holds air among fine strands of glass. Foam insulation traps gas inside closed or partially closed cells. Down jackets hold small pockets of air between feathers. Double-pane windows separate two sheets of glass with a sealed space. The materials look different, but the strategy is related. Prevent air from moving freely and make heat travel through a more difficult path. Bubble wrap contains that strategy in its simplest visible form. Each bubble is a tiny chamber. The air inside cannot move far enough to create strong circulating currents. Place those chambers against a cold or hot window, and the material adds resistance between the glass and the room. It is not equivalent to a professionally manufactured insulated window. It does not contain specialized low emissivity coatings. It is not sealed into a rigid frame. It has not been optimized for clarity, durability, ultraviolet exposure, condensation control, or decades of use. But it does something that bare glass does not. It adds a layer of trapped air. The modern story of bubble wrap begins in 1957 with two inventors, Alfred Fielding and Marc Chavannes. They were not trying to improve shipping. They were attempting to create textured wallpaper by sealing sheets of plastic together with air bubbles trapped between them. The wall covering never became a successful decorating trend, but the material's lightweight structure and insulating properties suggested other possibilities. Before bubble wrap became famous as protective packaging, it was promoted for use as greenhouse insulation. Only later did its ability to cushion fragile products become its defining commercial purpose. Sealed Air, the company founded around the invention, dates its origins to that failed wallpaper experiment and the shift toward packaging in the early 1960s. That history matters because it reveals something we now tend to forget. Bubble wrap was never only about cushioning objects. Its structure also changes how heat moves. The greenhouse application made sense. A greenhouse needs to emit sunlight while limiting the amount of warmth lost to cold outdoor air. Its transparent surfaces create the growing environment, but those same surfaces also create enormous heat loss. Add another layer containing trapped air, and the structure becomes easier to heat. The household version follows the same broad principle, although on a smaller and less controlled scale. A sheet of bubble wrap can be cut to the dimensions of a window and held against the glass with a light mist of water. The result is translucent rather than transparent. Daylight remains, but the clear view disappears. That trade-off is the reason the technique makes sense in some rooms and not others. A living room picture window may exist primarily for the view. Covering it in packing material would defeat part of its purpose. A bathroom window, garage pane, basement window, utility room, spare bedroom, workshop, or unusually hot west-facing window may present a different calculation. There, comfort can matter more than clarity. The choice between daylight and a perfectly sharp view is not new. For most of architectural history, windows were expected to balance light, privacy, weather protection, security, ventilation, and heat retention. Perfect transparency was only one priority among many. Modern architecture gradually made unobstructed glass a symbol of openness and quality. Larger windows made interiors feel brighter and allowed buildings to photograph beautifully. But large areas of glass also created a thermal cost. Engineers learned to reduce that cost with insulated glazing, reflective coatings, inert gases, improved frames, thermal breaks, exterior shading, and carefully calculated solar heat gain coefficients. A good modern window is not simply a sheet of glass, it is an engineered system. Older windows often lack those improvements. A single-pane, aluminum-framed window can transfer heat through both the glass and the highly conductive metal around it. Gaps in the frame can allow air leakage. Direct sunlight can pass through the pane and warm everything inside the room. Those are different processes, and it is important not to confuse them. Heat can pass through the window materials by conduction. Air can leak through cracks by infiltration. Sunlight can enter as radiation and become heat after striking indoor surfaces. Bubble wrap mostly addresses the first problem. Depending on its opacity and design, it may also alter some solar gain, but it does not repair a leaking frame or create a professionally sealed window assembly. That distinction is important because inexpensive techniques are often described in exaggerated terms. Bubble wrap will not magically reduce every energy bill. It will not solve an undersized air conditioner, a poorly insulated attic, leaking ducts, an unshaded roof, or air gaps around a damaged window. What it can do is add thermal resistance over the glass. And building science research supports the broader principle that adding window attachments can matter. The Department of Energy has studied and promoted storm windows, films, shades, and other products placed over or around existing windows. Low emissivity storm windows installed over poorly performing windows have been shown to reduce heating and cooling costs, with Department of Energy materials reporting estimated savings ranges of roughly 10 to 35% under suitable conditions. The precise result depends on the existing window, the climate, the building, and the product being used. A storm window is far more sophisticated than bubble wrap, but both illustrate the value of separating indoor air from an exposed pane with another layer. The Department of Energy also notes that storm windows can substantially reduce heat loss through windows, while modern low emissivity coatings can reduce energy loss by controlling radiant heat transfer. This does not prove that a sheet of bubble wrap will deliver the same savings as a certified low emissivity storm window. It will not. What it proves is that the original window does not always need to be removed before its performance can be improved. That idea has major economic consequences. Window replacement is expensive because the homeowner is purchasing far more than thermal resistance. The price includes manufactured glass units, frames, hardware, weather sealing, labor, removal of the old window, installation, finishing, warranties, transportation, and often contractor overhead. Those features have real value. A replacement window can improve appearance, operation, durability, noise reduction, air sealing, security, and resale appeal. A well-installed product can remain in place for decades. Bubble wrap offers almost none of that. It does not open smoothly. It does not preserve the view. It does not increase property value. It does not look finished. It is simply cheap. And cheap solutions become especially important when the person paying the energy bill does not own the building. This is one of the hidden problems of rental housing. The tenant pays every month to heat and cool the apartment, but the landlord decides whether the windows will be upgraded. The landlord pays for the capital improvement, while much of the direct financial benefit appears on the tenant's utility bill. Economists call this a split incentive. Neither side necessarily behaves irrationally. The tenant does not want to invest thousands of dollars into property that belongs to someone else. The landlord may see little reason to replace functioning windows when the tenant is responsible for electricity and gas. The window remains. The equipment keeps running. The utility bills continue arriving. This is where temporary and removable methods become more than internet curiosities. They occupy the space between a permanent renovation and doing nothing. Bubble wrap is only one of those methods. Removable interior storm panels can create a more finished secondary barrier. Cellular shades trap air inside their honeycomb-shaped construction. Window quilts combine fabric with insulating layers. Heavy curtains reduce the exchange of heat between the room and the window, especially when they fit closely around the opening. Exterior shutters and shades can block sunlight before it reaches the glass. Solar screens reduce the amount of solar energy entering through the window. Reflective films can alter solar gain, although compatibility with the existing glass must be considered. Simple air sealing around the frame may outperform all of them when leakage is the primary problem. Each method attacks a different part of the system, and this is where the story becomes larger than bubble wrap. For much of the 20th century, the response to uncomfortable buildings was to add more mechanical power. Hot building? Install air conditioning. Cold building? Install a larger furnace. Uneven rooms? Add fans, vents, ducts, or supplemental heaters. Mechanical equipment transformed daily life. Air conditioning made entire regions more comfortable and helped shape the growth of modern cities. But machinery can also hide weaknesses in the building itself. A poorly shaded window can be overcome by a larger cooling system. A leaking building can be overcome by a larger heating system. An uninsulated ceiling can be overcome by burning more fuel. The room becomes comfortable, but the underlying problem remains. Energy is spent continuously compensating for a weakness that might have been reduced passively. Passive design takes the opposite approach. Before adding equipment, reduce the demand placed on the equipment. Shade the glass. Control unwanted air leakage. Use insulation to slow conduction. Use thermal mass to moderate temperature swings. Ventilate when outdoor conditions are favorable. Orient openings to take advantage of useful sunlight while limiting excessive exposure. In a well-designed structure, the building performs some of the work before the machinery turns on. This approach is not anti-technology. It is what allows technology to operate efficiently. A smaller air conditioner serving a well-shaded and well-insulated room may provide better comfort than a larger unit fighting constant heat gain. A heating system in an airtight building can operate less often while maintaining a more stable temperature. The cheapest unit of energy is often the one the building never needs. The window is one of the clearest places to see this principle in action because its effects are easy to feel. Stand beside a single-pane window on a cold night, and your body may feel chilled even when the room's air temperature appears normal. Part of that discomfort comes from radiant heat exchange between your warm body and the cold glass. Stand beside the same window under intense summer sun, and the surrounding surfaces may feel hotter than the thermostat suggests. Comfort is not determined by air temperature alone. Surface temperatures, airflow, humidity, sunlight, clothing, and activity all influence how a room feels. That is why lowering the thermostat does not always solve the experience of discomfort near a bad window. The air may become colder while the surrounding glass remains thermally extreme. Adding an interior layer can change the temperature of the surface facing the room. Even when the total energy savings are modest, that warmer or cooler interior-facing surface may make the area feel more comfortable. This is one reason storm windows and insulated shades can create benefits beyond the number shown on the utility bill. They can reduce drafts. They can reduce cold surface discomfort. They can lessen condensation under certain conditions. They can make the temperature of the room feel more even. Bubble wrap may provide a crude version of some of those benefits, but it also introduces limitations. Condensation is one. Warm indoor air can contain moisture. When that air reaches a cold surface, water may condense. If moisture becomes trapped against wood, drywall, or dirty window components, it can contribute to mold, staining, or material damage. Any temporary covering should therefore be monitored. The window should remain accessible. The frame should be kept dry. The material should be removed if persistent moisture develops. Fire and emergency access also matter. A bedroom window may serve as an emergency escape opening. Nothing placed over it should prevent the window from opening quickly or reduce a required exit path. Lease rules may restrict unconventional coverings, especially when they alter the exterior appearance of a building. Plastic can also deteriorate with sunlight and time. It should not be assumed to be permanent simply because it remains attached. These warnings do not make the technique useless. They place it in the correct category. Bubble wrap is a temporary, low-cost insulating layer, not a building product designed to replace every function of a window. Its real importance is conceptual. It demonstrates that the thermal performance of a room can sometimes be changed without changing the heating or cooling equipment. A few millimeters of trapped air can affect the path heat must travel. A shade can prevent sunlight from reaching the interior. A thin seal can stop air from leaking around a frame. A curtain can create another pocket of relatively still air. None of these interventions is dramatic. That may be why they receive less attention than machines. Machines are visible investments. They have model numbers, efficiency ratings, installation appointments, financing plans, service contracts, and advertisements. Passive improvements often disappear into the building. Once installed, they simply reduce the amount of work required. There is no compressor sound when insulation performs correctly. There is no dramatic moment when exterior shade prevents the sun from striking a window. Nothing appears to happen. That is the point. The history of bubble wrap is therefore more than a story about an accidental invention. It is a reminder that materials can have valuable properties long before society decides which of those properties are commercially important. Fielding and Chavannes created a sheet of trapped air while searching for a decorative wall covering. The market ultimately remembered its ability to protect objects in cardboard boxes. But the insulation function never vanished. It remained inside every bubble. Today, that same structure can be found protecting electronics, filling empty package space, lining greenhouses, and occasionally covering the coldest or hottest window in someone's home. It is not elegant, it is not universal, and it is not a replacement for modern glazing. But it reveals a basic truth about energy that expensive systems can make easy to overlook. Heating and cooling are not only about producing warm or cold air, they are about controlling movement, the movement of heat through glass, the movement of air through gaps, the movement of sunlight into a room, the movement of moisture toward cold surfaces. Change those pathways, and the machine no longer faces the same problem. That is why the most important question may not be, how powerful is the air conditioner? It may be, God, does the room need so much cooling in the first place? Look at the afternoon sun. Look at the temperature of the glass. Look for gaps around the frame. Look at the attic above the room and the wall facing the weather. The answer may still require new equipment, but equipment should be the conclusion of the investigation, not the beginning. Because sometimes, the difference between an uncomfortable room and a manageable one is not another machine. It is another barrier, another shade, another seal, another pocket of air. Something quiet enough that once it starts working, you barely notice it at all.